Welcome to part 2 of our covalent compounds and VSEPR theory video. So let's talk about VSEPR theory. So VSEPR theory stands for valence shell electron pair repulsion theory. And so the letters in VSEPR are the first letters of these words. That's a pretty terrifying name, right? Like valence shell electron pair repulsion theory. It sounds really complicated, but the idea is actually really simple. And so the idea is that electrons are all negatively charged, and therefore electrons repel each other. And so if the electrons repel each other, then what that means is they want to spread the maximum distance from each other. In other words, they want to maximize the distance to minimize these repulsions between them. And by looking at the bonded atoms and lone pairs attached to the central atom, we can use this theory to predict the shapes of molecules. We can predict those molecular shapes. So there's 6 shapes I want you to learn from VSEPR theory, and the 6 shapes are going to be, if we have 2 electron groups, that means 2 items around our central atom. So we'd want to look at our central atom, and if around the central atom in our dot structure we have 2 bonded atoms and 0 lone pairs, then our shape is going to be linear. And so we have a drawing of right here. It looks like a straight line. So again, if our dot structure has 2 bonded atoms and no lone pairs about our central atom, it's going to be linear. Now, if we have 3 bonded atoms and no lone pairs, our shape's going to be trigonal planar. And so it's going to look like a flat triangle. So trigonal planar just translates into flat triangle. And our bond angles here are smaller. So we can only get 120 degrees between things instead of the 180. We're always trying to maximize those angles, maximize those distances between these repulsive items. But the problem is the more stuff we stick around our atom, our central atom, the smaller the angles have to become. So if we have just 2 bonded atoms and now 1 lone pair, we have a shape that's known as bent, or sometimes called bent 120 to reflect that 120-degree angle. And we'll be talking more about all these shapes in the lab, the VSEPR theory lab, if we haven't done it already. Now, again, we just look at how many bonded atoms and how many lone pairs are attached to our central atom. 2 bonded atoms, 0 lone pairs, so will always be linear. 3 bonded atoms, 0 lone pairs will always be trigonal planar. 2 bonded atoms, 1 lone pair will be bent. And moving on right here, this is where we actually expand into 3 dimensions. So 4 bonded atoms and 0 lone pairs is known as tetrahedral. We have a bond angle of 109 degrees. So if we look at on paper, one would think the maximum angle we could get between things would actually be 90 degrees, but that's not true. We can get bigger than 90 degrees by spreading out into 3 dimensions. And that's what we do. We get these 109-degree angles. We get almost 20 degrees more by spreading out into 3 dimensions. And we can also swap out one of these items for a lone pair. So we could actually draw in a lone pair right here on R. So that blob is meant to represent the volume those electrons occupy. And the dots are the electrons. And then on the water molecule right here, we can do something similar. So there's 1 lone pair. And then sort of eclipsed behind it, we can put in our second lone pair right there. So there's our 2 lone pairs on our water molecule. So now we have 3 bonded atoms, 1 lone pair is going to be trigonal pyramidal, and 2 bonded atoms and 2 lone pairs is going to be bent 109 this time because we have different angles, we have more stuff. So one of the things you're going to want to master in this chapter is going to be drawing in 3 dimensions. And so I want to point out, if you want to draw something coming towards us, so here's our central atom on our molecule, we're going to use a sort of a wedge type structure to show that this is coming out towards us. So see how it's skinnier? It's a bit hard to draw with the mouse. It's skinnier back there and it gets wider. That's meant to show it's coming towards us. And any bond that's shown as a regular old line is meant to represent it's in the line of the paper, or in this case the plane of the screen, rather, the plane of the paper or the plane of the screen. And then right here there's another one in the plane, and then we have another one right here that's pointed away from us. So that dashed line is meant to show that other atom sort of disappearing into the background. So we have 1 atom or two atoms rather, that are in the plane of our screen or in the plane of the paper if we were drawing this. We have one that's coming towards us, and we use this different type of bond, the wedge, to show it's coming towards us, and this dashed one's meant to show it's going away from us. So my drawing here is pretty crappy. It's the best I could muster with the mouse. And we go over this in lab. We'll try to make some nice, prettier drawings, and you'll also be practicing not only drawing dot structures, but predicting VSEPR shapes. And again, in order to find these VSEPR shapes, you need to know what's going on with the dot structure. So you need to be able to look at our table here. Now, right here, if we look at the dot structure for nitrogen trifluoride right here, we have single bonds all over the place and a lone pair. So around our nitrogen, we have 3 bonded atoms. So I'm going to abbreviate bonded atoms as Ba, so 3 bonded atoms. And then we have 1 lone pair. So our first step here to finding the shape is that we have to draw the dot structure. And so around our central atom, around our nitrogen, we have 3 bonded atoms and 1 lone pair. So if we refer to the previous page, 3 bonded atoms and 1 lone pair is always going to be trigonal pyramidal. So the shape of this one will be trigonal pyramidal. Now if we look at this structure here, around our carbon we have 2 bonded atoms and we have 0 lone pairs. So notice it's 2 bonded atoms, not 4. Although we have 4 bonds, there's only 2 actual atoms bonded. So again, although we have 4 bonds, we have just 2 bonded atoms right here. And so if we look around our carbon, we also have 0 lone pairs. Referring back a couple pages, we see that 2 bonded atoms and 0 lone pairs is always linear, so our molecule right here is going to be linear. So I'd like you to now end the video and please complete question number 6. Thanks for watching. Goodbye.